Sometimes, even big discoveries can seem pretty modest at the time. For thousands of years, people have been studying the sky. Night after night, the stars become familiar to them, appearing in the same formation each night. These patterns become our constellations. Almost all points of light stayed within their constellation and remained in the same position each night. But a handful wandered. Ancient Greeks called these wandering stars planets, and Romans named them after some of their gods: Mercury, Venus, Mars, Jupiter, and Saturn. Galileo Galilei was the first to look at these planets through a telescope. As he looked at Jupiter, he sketched what he saw. He drew one large body in the middle and 3 small points off to the sides. He first thought these might be fixed stars, far away, but in the same direction as the planet. Intrigued, he watched them each night, and for 2 months he drew what he saw. Over time, a new one appeared, and they all appeared to be wandering too. But they never seemed to stray too far from Jupiter. He then realized they were not distant stars, but moons. We now call them the Galilean moons of Jupiter. He moved on to observe Saturn. There was one large body in the middle again, but this time he saw a smaller object off to each side, much larger than what he saw around Jupiter. He was confused by what he saw. They were definitely unusual. He even admitted that he had no idea what they were, but he sketched them anyway. Over the next few nights, he observed the same thing. The 2 side objects didn't wander at all. He thought that maybe one always preceded Saturn, and the other always followed it in the planet's orbit. When he observed Saturn years later, he thought it may even have 2 handles attached to it. We can forgive him for his confusion when we consider that his observations were made with one of the first telescopes ever built. "45 years later, telescope technology improved to the point that a Dutch astronomer, Christian Huygens, was able to see that Saturn was actually surrounded by rings. Even today, telescopes on Earth have trouble seeing the rings in great detail. Light rays from distant stars and planets come through our atmosphere and are bent this way and that before the light even reaches the ground. It's like looking at an object at the bottom of an agitated swimming pool. To help see Saturn in greater detail, we use a video camera to record dozens of images each second. Computers then find the ones that look the sharpest. After combining them, they create a better image. You may first notice that the rings are not equally bright. the inner and outer regions are dimmer than the center. And there is what appears to be a dark break in the rings. It's called the Cassini division, and it is wider than the United States. For many years, images like this convinced astronomers that there were just 3 rings. The part outside the Cassini division was called the A ring, and just inside it, the bright B ring. Much closer to Saturn is the faint C ring. To learn more, NASA, the European Space Agency, and the Italian Space Agency built the Cassini-Huygens spacecraft to send to Saturn. It took the spacecraft 7 years to travel over 2 billion miles. To help it on its journey, it used the gravity from Venus, Earth, and Jupiter to accelerate it through space. Finally, in 2004, the 22-foot-tall craft joined over 60 moons and the ring particles around Saturn. We can see that the rings span over 150,000 miles from edge to edge, and yet they are only about 30 feet thick. If you tried to make a scale model of the rings using a single sheet of notebook paper, it would need to be 1,000 times thinner to be correct. By bouncing radar signals off the rings, we found that the rings are made of many particles, ranging in size from specks to icebergs the size of a small house. But even with our best telescopes and space probes, they're too small to be seen in any pictures. They are made mostly of frozen water with just a tiny amount of dust. Each particle speeds around the planet like a miniature moon, going about 50,000 miles per hour. Each one is in free fall, but they're traveling so fast that they never spiral down into Saturn. They keep missing the planet. One of the first things Cassini did was try to learn more about Saturn itself. Saturn is one of the 4 gas giant planets in our solar system. And scientists know that it is made out of gas because they use spectrometers, instruments that use light that is reflected off of Saturn to identify what elements and materials are there. Cassini has 5 different spectrometers. And with them, we know that Saturn is mainly made up of dense hydrogen and helium gas. Down inwards into the planet, toward the core, there are layers of liquid and metallic hydrogen and helium. And eventually, they may lead to a rocky core. We don't know what's there for sure yet, but we do know what's in the upper atmosphere. It has clouds of ammonia ice, which help make the planet the hazy yellow that it is. And occasionally in this layer, a bluish spot appears. It's lightning, over 100 miles in diameter. It produced almost 3 billion watts in just a single second. but perhaps the strangest storm can be found at Saturn's north pole. It's an enormous hurricane-like storm in the shape of a hexagon, and each side of it is wider than Earth. Scientists use models of Saturn's atmosphere in the lab to help understand how this storm gets its shape. They put in a narrow flow of air, and what do they see? A hexagon. This airflow is similar to the jet streams here on Earth that affect our storms. Looking out to the ring system, we can see that there are more gaps in the rings than previously thought. However, the Cassini division isn't empty. It is actually full of particles. There are just fewer particles here than in the main rings. The more dense the particles, the brighter the ring. Farther out is the N-key gap in the A ring. Particles are forced out of this area by the gravity of a small moon shaped like a flying saucer. This moon, named Pan, probably started out as a massive core. It rapidly grew, drawing other particles in by the force of gravity, and eventually formed the odd shape we see today. Here, Pan stands out as rays of sunlight cast its long shadow onto the A ring. Images like this are only possible when the edge of the rings are aimed directly at the sun. During this time, sunlight skims along the upper and lower surfaces of the rings, making any tall features noticeable. Let's take a look at another gap during this time. Farther out, the Keeler Gap is lined with wave-like peaks, all driven by the small moon in the gap, named Daphnis. These aren't the only peaks we see in the rings. In the B ring, the densest and most massive ring, we find hundreds. They stretch for 750 miles and tower 1.5 miles above the ring plane. This is quite amazing when you remember that the ring's thickness is usually only 30 feet. These peaks are probably formed by even smaller moons, or moonlets, too small to be captured by Cassini's cameras. Without surrounding moons or moonlets, ring particles will bump into each other and spread out. So when scientists saw this remarkably narrow ring, the F ring, they knew that there must be a nearby moon. There are actually 2 moons here, Pandora and Prometheus. Pandora orbits just outside this ring, while Prometheus orbits inside it. They are called shepherd moons because they herd the ring particles, keeping the ring narrow. The many narrow ringlets we see throughout the rings may be due to small shepherd moons embedded within, too small to be seen in our images. As Cassini orbits Saturn, it observes the F ring up close and sees that it is constantly changing its appearance. Kinks and channels appear when the shepherd moons and moonlets interact with the ring. During its orbit, Prometheus gets close enough to the F ring that it draws out a streamer of material. In 2013, the Cassini spacecraft captured this remarkable image of Saturn eclipsing the Sun. Even though this is the night side of the planet, we see it illuminated by light reflecting off the rings. Just outside of the edge of the main rings is a small bluish object. You have to look close to see it. It is not one of Saturn's moons. It is much farther away than that. It is planet Earth, seen from almost 900 million miles away. From this view, we now see that there are two additional rings of Saturn. Outside the A and F ring is the dim G ring, and farther out still is the extremely wide and diffuse E ring. The ice dust in this ring is easily dispersed by impacts from micrometeorites. This ring should have been lost long ago. To understand what's replacing it, we have to look inside the E ring. When we do, we find Enceladus, a moon that's just over 300 miles across. Its cracked, icy surface doesn't have a lot of impact craters on it like our moon. But since meteor strikes are common, something must be erasing them over time. This was a mystery until Cassini looked at the night side of the moon. It found volcanoes on Enceladus. They weren't shooting out lava, but jets of water ice into space. This is what replaces the lost ice in the E ring. Cassini flew through one of these clouds of ice and found that it contains traces of nitrogen, one of the core chemical elements needed for life. Could bacterial life thrive in the liquid water beneath Enceladus's surface? Eventually, scientists discovered that other planets in our solar system have rings. In fact, all of the 4 gas giant planets have ring systems. Faint rings around Uranus were discovered by the Kuiper Airborne Observatory in 1977. This started the search for rings around Jupiter and Neptune. But the discovery of Jupiter's rings had to wait until it was visited by Voyager 1 in 1979. Neptune's rings were not verified to exist until Voyager 2 imaged them about 10 years later. What about planets outside of our solar system? Planets that orbit other stars? Do they have rings? These exoplanets are too far away to be studied in great detail. But we can understand some things by looking at their host star. Throughout the planet's orbit, detectors can sometimes see the starlight dim. This is because the planet is in the way of the telescope, blocking out some starlight. By measuring how much light is blocked, we can determine how large the planet is. Using another method of exoplanet detection, we can determine the planet's mass. Along with its size, its density can be calculated. How can finding the exoplanet's density help us detect if it has rings? If the rings are tilted in the right way, they can block starlight, just as planets do during transits. This extra blocking of light could make the planet appear to be 10 times larger than it actually is. This would give a density value less than the actual density of the planet. Exoplanets found with very low densities could be a sign that the planet has a ring system. For now, we have Saturn's rings to study as we try to find the answers to help understand the mysteries of the universe. Cassini has provided views of Saturn, its rings, and its moons with clarity far exceeding that of the Hubble Space Telescope. With Cassini, we are seeing more than we ever thought possible. We have truly come a long way since Galileo's first drawings of Saturn.